Okay, guys, this question asks you to get all of this information to draw a Lewis structure and determine electron geometry, molecular geometry, bond angles, whether it's polar or nonpolar. And if you're in general chemistry, they want you to go a little further: intermolecular forces, hybridization, number of sigma, number of pi bonds. Okay, so let's start off with it. It's CH4. And so with CH4, what I want to do is I want to count up all the valence electrons. The valence electrons for CH4 are 4 from the hydrogen and 4 from the one carbon. So hydrogen times is 1 times 4, that's 4, plus the 4 from carbon, you get 8. Okay, the next step is to arrange the atoms as symmetrically as you can on the paper or on your drawing pad. And we're going to go ahead and put the C in the middle. CH4 was the compound. And so the first atom is usually the central atom. Okay, now what we want to do is we want to draw a single bond between all of the atoms. Once we've done that, we would remove those electrons from our valence electron count. 4 bonds, 2 electrons in each bond, that's 8 electrons. We have no more electrons left. And now we have octets around everything. So carbon has 4 bonds, each hydrogen has a single bond, so we consider that to be octets. All right, now for electron geometry and molecular geometry. There are 4 geometry groups around that carbon. So each bond is a geometry group, and 4 geometry groups around a central atom means that it's a tetrahedral electron geometry. We also notice there are no lone pairs of electrons, and since there are no lone pairs of electrons, the molecular geometry is also tetrahedral. With a tetrahedral geometry, for electron geometry comes 109.5 degree bond angles. So the bond angles are 109.5 degrees. Is the molecule polar or nonpolar? Now, I'm going to go ahead and say that if there are bond dipoles, then they all cancel each other out. A perfectly symmetrical structure would do that, and tetrahedrons are perfectly symmetrical. And so because of that symmetry, we would get a molecule that is non-polar. Now, a quick and dirty way to determine whether the molecule is polar or non-polar is to look around the central atom. Ask yourself, is every geometry group exactly the same? And remember, we had 4 geometry groups. Each geometry group is a bond to a hydrogen atom. So yes, all the geometry groups are the same. If all of the geometry groups around a central atom are the same, then you can say that the molecule is nonpolar. But that is, especially in general chemistry, that is quick and dirty, and you will get it wrong maybe 1 out of 20 times. Okay, so we're going to go into examples that explain that later. So if you're in introductory chemistry, that's all you need to know. If you're in general chemistry, we'll go a little further. Okay, so once we've decided that it's nonpolar, we could list the intermolecular forces. Well, of course, all molecules have London dispersion forces, so we'll list those. But since it's nonpolar, it won't have any of the other forces. It doesn't have any dipole-dipole forces, nor does it have any hydrogen bonding. With tetrahedral electron geometry, we could say then that the hybridization is sp3. That geometry predicts the hybridization as well. With the number of sigma bonds, we just count up the single bonds, 1, 2, 3, 4 single bonds. So we've got 4 sigma bonds. And since there are no double or triple bonds, we have 0 pi bonds. Okay, that's it for this molecule.